Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking a bit about resistivity. This is not to be confused with resistance, which we have already kind of defined in our video on Ohm's law. This is actually another term called resistivity. So you might be wondering right off the bat, how are these things related? You'll recall that in the microscopic view, the current essentially is going to be given by the, or maybe I should say should be proportional to the electric field which is applied to our conductor times the cross-section area of the conductor. And the proportionality constant is actually called the conductivity, but it's related to another term called the resistivity as follows. So I is equal to 1 over rho times E times A. So this is sort of like your microscopic view of current, where this term right here is the electric field, or electric field strength. Remember that that is basically going to be the voltage drop divided by the length over which that voltage drop is being applied. This right here is the cross-section area of the wire. And then this is what's called resistivity. And so this resistivity is a property of the material that's being used. So you'd have a different value of resistivity for, let's say, copper than you would for gold or for tungsten or aluminum or what have you. So I'm just going to label that as material property. And then note that this equation could be rewritten as I is equal to 1 over rho, and then A, we could just put the A over here, and the L length is your basically the length of your conductor, the length of your wire, in other words. And then all of this is times delta V. But Ohm's law says, Ohm's law says that delta V should be equal to I times R. Or in other words, that I is delta V over R. So looking at this stuff, this is the over R. This right here must be the over R part. So the conclusion that we would draw is that the resistance R must be the resistivity rho times the length divided by the cross-section area. So length of our conducting element, our wire, or whatever you have, cross-section area of the wire or conducting element or whatever you have. So this gives us our relationship. This means, by the way, resistivity has or must have units of ohm times meter. To put this in perspective, if I have a wire like this wire will have some resistance to it, and that resistance is given by a combination of how long the wire is, what the wire's cross-section area is, and then what the material is made out of. So material determines rho. This is very much, I should say very much like, but it's it's like and at the same time unlike the equations we've had so far for capacitors and for springs for that matter. So let's write those three equations out very quickly. The spring constant Ks was Young's modulus times cross-section area divided by the unstretched length. And Young's modulus, Y, was a material property. So material property, essentially it's how stretchy is it. But the actual term is Young's modulus. And so for a given material, we might, for an introductory physics class, treat Young's modulus as if it's a constant. Okay? For capacitors, we have C is equal to kappa times epsilon naught times the area divided by the distance between the plates. And this right here, again, is a material property. The kappa and epsilon naught are sometimes thrown together as a term epsilon permittivity, and so collectively they're a material property, but it's really the kappa that's changing. This is what's called dielectric constant. And then we rewrite our resistance. Should write here, this is a capacitor. And then for our resistor, we have R is equal to rho times essentially a length divided by an area. So again, this term right here is your material property. Okay, so how is this like and unlike these other two equations that we've had so far? Well, for the resistor, you notice that the length term is in the numerator and the area term is in the denominator. For the other two, the area term is in the numerator and the length or distance term is in the denominator. So it's similar. It has an area, it has a distance, and it has a material property. It's different in as much as the length and area ratio is sort of reciprocal from the other two. This will have some significance when we go to talk about series and parallel circuits, for what it's worth. There's one other thing that should be said about resistivity, but before I get to that, it might be worth kind of like noting what are some common values for resistivity. So I've copied a table out of the OpenStax college physics textbook. That one specifically because it's the open, sort of like open education resource book. Depending on what book you're using, your table may be a little different, but the values should be more or less similar for a given material. So for example, like right now we're using the Survey and V textbook for my online physics course at CVCC, and we use, I believe, Knight, Jones, and Field was what we'd been using before there, and I think that's what's being used at like University of St. Thomas for their college physics and so on. So but this table comes from the OpenStax college physics textbook. And these are all conducting materials. And you'll notice that for each of these, the kind of salient point is that this is a very small number. So times 10 to the minus 8 for all of these. Compare that to insulators, and again, same source. Compare that to some insulators where these resistivities are times 10 to the 14 or 10 to the 13, 10 to the 15, 10 to the 16, like really big numbers by comparison. So that is one way of measuring, like, is this a conductor or an insulator? It's kind of like, what is the resistivity? Now, with all that said, These resistivities are kind of at some particular reference value because resistivity is temperature dependent. And the equation that we use for that is that rho is actually equal to rho naught times 1 plus some value of alpha times the actual temperature minus the reference temperature. So these are really rho naught values. And these are basically at a temperature of 20 degrees C. That basically means that the T naught value is 20 degrees C. For what it's worth, this temperature right here is in Celsius. This right here is reference temperature. And so this is sort of like a temperature at which you've done a really thorough job of measuring your resistivity, also in degrees C. This right here is resistivity at the reference temperature. And then the alpha term is what's called the temperature coefficient. So this is what's called temperature coefficient, or sometimes temperature coefficient of resistivity. Now, for most materials, as the temperature increases, the resistivity also increases. But for some materials, mostly the semiconductor materials, the opposite is true. And so alpha is positive for conductors and insulators and whatnot, but it's actually negative for the commonly used semiconductors. Basically means that the semiconductors can be switched to being from being basically insulators to being conductors by changing this property of the material. All right, so again, using the OpenStack source, here are a few alpha values for conductors, and you see they're all positive. And then down here we have a set for semiconductors, which are all negative. They all tend to be on the order, for all these materials, they're all on the order of 10 to the minus 3. Essentially, what that means can be best explained by a quick example. All right, so I've got some resistor. It has a resistance of 100 ohms at room temperature, which again is 20 degrees C. And what we want to know is what the hot resistance will be if it operates stably at, let's say, 220 degrees C, given this temperature coefficient. And so you could say that like R hot over R cold should look like the ratio of rho hot over rho cold. And that ratio in turn is just going to be 1 plus alpha times T minus T naught divided by really just 1. Basically what I've done here is I've assumed lengths, areas, and T0 resistivity is the same in both cases because they should be. Yeah, it gets longer and wider, but that's part of what this coefficient is taking account of. So basically this just ends up looking like 1 plus alpha times T minus T naught. So plug in our numbers. What we should get is that the ratio is 1.9, and therefore that the hot resistance is 1.9 times the cold resistance, or 190 ohms. And so you have a higher resistance at hot, and that's also means you draw less current, use less power.